Very, very difficult to start with. Not really. All right, we have a car. That car is traveling at a rate of 60 miles an hour from t equals 0 to t equals 2 hours. So here is 60 miles an hour. There's our constant rate. There's 2 hours. There's the point at 2 hours. How far did the car travel during those 2 hours?
$120 miles.
120 miles. How many of you agree with that?
I agree.
Oh, good. One person.
All of us.
Everyone agrees. Perfect. That's what I was hoping to hear. Right. If I went 60 miles every hour and I didn't change my speed and I went for 2 hours, it seems reasonable that it should be 120 miles. You're right. Good work. All right. Look at you guys go. All right. Now, I've changed into my other car, which is magical. And so I'm going to go 60 miles an hour for the first hour. There's hour 1. Right? And then somehow, magically, at the exact instant of 1 hour, I increase my speed to 70 miles an hour for the second. How far did I go during those 2 hours?
130 miles.
You guys agree with that or no?
I do.
You're right? 60 miles in the first hour because I went 60 miles per hour, and 70 miles in the second hour because I went 70 miles an hour. Easy, huh? Wondering why didn't we start the year with this? This is so much easier. All right, now it's slightly more difficult. Starting off at 60 miles an hour, and I am increasing at somehow a constant rate over those 2 hours from 60 miles an hour to 70 miles an hour. I start at 60, I finish at 70, and no starting, no stopping, no like stepping on the gas hard and then slamming the brakes on. A complete constant acceleration of 10 miles an hour total over those 2 hours. How far did I go?
Would it be 130?
It would be 130. Does that sound right to people or no? It's okay if it doesn't. Maybe that's not right. What do you guys think? 130 miles?
Sure.
Yeah, it is. It's 130 miles. Good or no?
Not really.
Not good? Not happy. I mean, what's the average velocity if I start at 60 and finish at 70 and I increase at a constant rate?
65.
Should be 65, right? And so if I average 65 miles an hour for those 2 hours, I should have gone 130 miles, right? 65 in the first, 65 in the second.
Oh, okay, got it.
Yeah. Everyone good there?
Yeah.
All right. Cool. All right, now we're going to make this even more difficult. This is my new graph of how fast I was going. I started at 60 miles an hour and I went a little faster for a while, and then I slowed down, and then I went even faster, and I finally finished my 2 hours of driving. How far did I go in those 2 hours? Any guesses? Silence out there. All right, let's go back to the beginning. How far did I go?
120.
All right, okay, 120. how is that related to my graph?
The x value times the y value.
Yeah, that's true, right? It's this x value, 2, times this y value, 60, right? Which was a constant y value. And what does multiplying this by this tell me geometrically?
Area.
It's,
If you want to make it
yeah, if I were to make this into a rectangle, that would be the area underneath that function, between that function and the x-axis, right? True?
yeah.
All right, so this distance that I traveled was the area underneath my velocity graph. What about this distance that I traveled? If I were to turn this into 2 little rectangles here, this one has an area of
60.
and this one has an area of
70.
70, and 60 plus 70 is amazingly 130. Yeah, everyone good with that? The area underneath this velocity graph gave us a total distance, right? Which makes sense. Velocity times time, right? What's velocity? Velocity is miles per hour. If I multiply that by hours, what should I get? Should cancel out and give me a total number of miles, shouldn't it? If I find that area, right? Isn't that how units work? Miles divided by hours times hours would be miles.
Yes.
Yeah. What about this one? We said 130. We should be able to check that now, because what shape is this here?
Triangle and a rectangle.
Yeah, it's a triangle and it's a rectangle, or even I mean, we could do it as a triangle and a rectangle, but also if I flip this on its side, it's I mean, it doesn't have to be flipped, but it's a trapezoid, right? 2 parallel bases. Yeah. And then a height to it. So whether we do it as, we could do it as a rectangle and a triangle if we want. The rectangle has an area of what? 60 times 2, right? 120. And the triangle is 10 times 60 divided by 2, which would be not 10 times 60, 10 times 2 divided by 2. What am I doing? This is 2. 10 times 2 divided by 2 should be 10, which would give us 130, right? Even though that looks like a 101 there. 130. Or if I'd done it as a trapezoid, it would be 60 plus 70, average of the bases, right? Divided by 2 times the height, which is 2, which would give us 130. Good or no?
Good.
All right, off to a good start. So how far did I go during these 2 hours?
I
At
don't
least,
know.
okay, at least by looking at the graph, we could describe how we could figure out how far it went.
We can think of each change in concavity as one area that we need to find.
All right, so okay, let's go even more basic than that. If we found the area under it, right? Not just like this piece of it or something, but if I found the entire area underneath it, wouldn't that be how far we went?
Yes.
Yeah. And so what we need to do is what you were just starting to say, is we need to figure out a way to come up with what that area underneath the curve is. And so you were saying treat each piece of concavity of it, so like maybe from here to here-ish and from here to here-ish, and then it switches back, and figure out this area and figure out this area and figure out this area. Still going to be a little difficult to figure out those areas though, isn't it?
Yeah.
Yeah, I mean, in any way that we're going to do this at the moment, we're going to have to just get some sort of approximation, right? Anybody have a good idea of how they'd like to approximate it? What could I do? I mean, what are some shapes that I know easily how to find the area of? Like really easily.
You could draw like little rectangles.
All right, draw little rectangles. All right, so if I drew some rectangles, I'm going to draw some rectangles. There's a rectangle. There's a rectangle. There's a rectangle. Like this. Rectangles inside of here.
You could.
Clearly I could. I'm doing it right now.
Is this
Might
Mario
it-
Kart now?
Now we know the area. No, you're right. Okay, we want to do some rectangles, but not in like a snide and sarcastic way like I'm doing it. We want to draw some rectangles in here. And so there's some different ways that we can draw some rectangles in here. Let's assume that as we're driving along here in these 2 hours, let's say every 15 minutes, let's say, I looked at my speedometer and said, oh, now I know exactly how far I was going in those at this exact moment. So what we're going to do is we're going to break it down, break this entire larger interval into a bunch of different subintervals. And we're going to sketch some rectangles that go sometimes underneath the curve and sometimes extend a little bit beyond the curve. And rectangles are easy to find, right? If we knew that this is a quarter of an hour, this would always be 0.25 for the width of the rectangle. And wherever we happen to draw the line up here for our rectangle, let's suppose it was here, we would know the height of that rectangle and we could find that area. And it wouldn't be perfect, right? But it would at least give us an approximation. I assume that, I'm not sure who was talking, I assume that's sort of what you meant, more like this than my random annoying rectangles.
Yes, that's more what I meant.
Perfect, yes, okay. So we're gonna do this in a couple of different ways. And this is actually what we're gonna do for now, is we're gonna learn how to estimate the areas underneath these curves and practice doing that a little bit. So the first method that we're going to use is what's called the left rectangular approximation. So a left rectangular approximation says divide your interval up into however many subintervals you want. So I've just divided it up into 8 total subintervals. And it says take the first subinterval. So here's my first subinterval, right? From 0 to a quarter of an hour, 0 to 15 minutes or 0.25 hours. And go to the left side of that subinterval, find the height of your function, and draw a rectangle. That should be easy to find the area of, right? 60 times 0.25. Got part of it. Then go up to the height at the next subinterval's left endpoint, which would be right here, and draw a rectangle there. And then do it again with the next one. So this left endpoint should be up here. I should draw a rectangle that looks something like this. And then I should be here and draw another one, and I should be here and draw another one, and here and here and there, until I've drawn 8 different little rectangles underneath my curve. And we'll note that some of those little rectangles end up leaving off some area, and some of them end up extending over. And so some of those will cancel each other a little bit, right? And we'll get a decent approximation for the area underneath this curve. This is called a left rectangular approximation method. Really wish I could get another color in here. Why isn't my toolbar working? Keeps showing up and then disappearing. Any questions on that?
If this was like a sine curve or a cosine, would the rectangles perfectly cancel each other out, like the extra space?
Not necessarily.
Okay.
It depends on the specific intervals that we use. They might, but it just sort of depends. Yeah, everyone good there or no? All right. Oh, I wanted to say one other thing about this. What happens when our function is increasing? So for a left rectangular approximation, if f is increasing, what does that tell you about your approximation?
You're capturing less area.
Yeah, the approximation is going to give you less area. The approximation is an underestimate. And if f is decreasing, that's going to tell us that we are getting an overestimate. And so this is actually fairly important because they will ask you to approximate something using like a left rectangular approximation. And then based on what you know about the function, they'll say, is your approximation an underestimate or an overestimate? Well, you'll say, well, function was increasing, so it's an underestimate, or the function was decreasing, so it's an overestimate. Yeah. Good or no?
If it was increasing and decreasing numerous times, would you just say under or over based on how many times it's increasing or decreasing?
Not necessarily. Then it has more to do with how rapidly it's increasing or decreasing. They will likely not ask you that if the function or if they did ask you that if the function increased and decreased, you'd probably be able to just say that it's not able to be determined because the function both increases and decreases on the interval that's given to you.
Okay.
Yeah. All right. Next method is the right rectangular approximation method, which seems almost exactly the same as the left, except once we divide it into our subintervals, we just start on the right-hand side here. So I'm going to draw this rectangle at the right endpoint of the rightmost subinterval. And then I'm going to draw another rectangle from the rightmost endpoint of the next subinterval, and then another one, and then another one, and then another one, and another one, and another one, and another one. And you probably noticed that looks about as accurate as the left one did, just sort of in the opposite direction. And it's exactly the same, except you start at the right endpoints. And so we would say, for this, if f is increasing, what do we end up with now? Our rectangles, when the function's increasing, went outside of our function, right? It would give us an overestimate. And if f is decreasing, it should be an underestimate. Good or no?
So could you average the two?
You could average the two, yes. And we're going to talk about averaging the two of them a little bit in a few minutes. And it will give you a better approximation for sure, but it doesn't necessarily make an exact area underneath the curve because we don't know how rapidly, we could have a function that does this, right? And then like increases again really rapidly, in which case you're, the amount that you're going to be over may be very different than the amount that you're going to be under on each side. So, does that make sense?
Yeah.
Yeah, okay, cool. All right, any questions on the first two? We're going to practice doing them with functions in a little bit, but conceptually, does that make sense?
Yeah.
All right. So the next one we're going to do is the midpoint rectangular approximation method. Hold on one second. All right, so for the midpoint rectangular approximation method, all we're going to do is we're going to take all these same subintervals we're going to find the midpoint of each one. Go up to our function at that midpoint and draw a rectangle that takes the entire subinterval, but crosses through at the midpoint of that subinterval. So up about here, and a rectangle, and another rectangle, and another rectangle, and another rectangle, and another rectangle. And another one. And we'll note that in this case, when the function is, let's say, decreasing, we have some portions of it that we miss, but also some portions that go over. And so whether it's increasing or decreasing isn't going to tell us anything about whether this is an underestimate or an overestimate. But if we look at it, it sure looks like the pieces that are outside of the function and inside of the function that's missing are a lot less than they are with the left and the right rectangular approximations. True?
Yeah.
Yeah. So we will say this is a better approximation than the left or the right. Okay. So if you can do a midpoint, it's going to give you a better approximation than the left or the right will. Good or no?
Good.
All right. That is our first three methods. There's going to be one more. There's really two more that get used fairly often, but we're only going to talk about one more because only one more of them is on the AP test. But we're going to practice these three first, just with a problem or two here. So what we want to try to do is approximate the area underneath the curve f of x equals x squared from 0 to 3. And we're going to use left, right, and a midpoint rectangular approximation to try and do this. And I guess we should start with the left one. Yeah.
Sure.
All right, so let's do that. So if we start with the left approximation, and we're doing the interval from 0 to 3, that means we're dividing up into 3 subintervals, it says. So 0 to 1, 1 to 2, and 2 to 3. Everybody good with that? So we're dividing it up 0 to 1, 1 to 2, and 2 to 3. All right, so for our left approximation, we start off with a height of 0 at the beginning of our first subinterval, which actually gives us really no rectangle, right? So 0 times, this is our left, 0 times the width of 1, and then we're going to add the next rectangle. The next rectangle should start at 1, which means we're going to go up here to 1 squared or 1 and get this rectangle, which has an area of, let's see, 1 unit high times 1 unit wide, right? And then the last rectangle between 2 and 3 should look like this. And that has a height of what? 4, right? 2 squared, and a width of 1. And so if we do this as a left approximation, what do we end up with?
Five,
which we know is way off, right? How do we know it's way off? Well, this function is only increasing on this interval, and therefore this is an underestimate, right? Because it's a left rectangular approximation, and the function is increasing. All right, so we'll say it's underestimate because it's increasing. And we can see that. I mean, obviously, the first one we left off all of this, and the second one, right, we left off all of this, and the third one we left off all of this. Clearly, we missed quite a bit of area. True? Everyone okay with that?
yeah.
All right. Let's do a right approximation for this, a right rectangular approximation. So same situation, 0 to 1, 1 to 2, 2 to 3. But this time we're going to use the right endpoint. So we're going to start at 3 and go to 2. So up here at 3, we have a height of 9, right? And we're looking at a really nice looking rectangle like that. What's the area of that rectangle? It should be the height, which is 9 times the width, which is 1. Okay. And what about the next one? Next one should start here, which gives us a height of 4 and a width of 1. And then the last one should be this one, right? With a height of 1 and a width of 1. And what does that give us? Gives us 14, which we know is an overestimate because this function is increasing. Good or no?
Yeah.
All right. Let's do one more. Let's do the midpoint. All right. Before we do the midpoint, let's think about this. What do you guys think? Do you think this is, if 5 is closer to the actual value or 14 is closer to the actual value? Just out of curiosity.
Probably 5 because the curve's going downwards.
Okay. So you think at 5. How many of you also think 5? Anybody else? Anybody think 14? Anybody even care? Doesn't sound like it. Bummer. All right. All right. Well, we'll figure that out in a minute because I'll tell you what the exact value is in a minute or two here. So let's do the midpoint rectangular approximation. So same thing, 3 subintervals, 0 to 1, 1 to 2, 2 to 3. But this time midpoints. So we got to go at the midpoint of 0 and 1, which should be a half, and make a rectangle there. And the midpoint of 1 and 2, and make a rectangle there. And the midpoint of 2 and 3, and make a rectangle there. And so each of them has a width of 1, right? But they all have different heights. So what's the height of the first one? Our midpoint was 1/2, right? So what is this up at? Should be at 1/2 squared, right? Or 1/4, 0.25, right? What about the next one? That was at 3/2, so that should be at 3/2 squared. And then this was at 5/2, so that should be at 5/2 squared. So that's going to give us a fourth plus 9/4 plus 25/4, which is what, 35/4 or 8.75, right? If we put that into a decimal, which is not necessary, but just gives us a better idea of what it is. It's 8.75, right? And you think that's a better approximation than 5 was or than 14 was?
Yes.
Yeah, it definitely is. I'll tell you that the actual value of this, anybody know the actual value of this? That's right, you were all about to say it. It's 9. There are exactly 9 square units underneath the parabola f of x equals x squared from x equals 0 to x equals 3. Exactly 9. And so we can see that 8.75 is a pretty darn good estimate, right? Only off by a quarter. Let's think a little more about this. What would happen, or how could we make it happen that we get a better approximation just from using one of these 3 methods? Any thoughts on how we could get a better approximation?
Smaller rectangles or thinner rectangles rather?
Yeah, thinner rectangles. So like instead of having the interval, having 3 subintervals from 0 to 3, maybe put 6 subintervals, right? 0 to a half to 1, 1 to 1.5, 1.5 to 2, 2 to blah, blah, blah. Right? 6 subintervals. The arithmetic would be a little more annoying and there'd be a little more arithmetic to do, but it wouldn't be impossible, right? And we were already at 8.75, like we could get even I mean, even better, right? If we got more subintervals, we even closer to the actual value of 9. What if we put in, 50 subintervals in between here? How close do you think we'd be?
Very close.
Extremely.
Very, very close, like off by probably something like 0.00001 or something like that. Imagine if we put like, 1,000 subintervals in there, or 1,000,000 subintervals in there, or how many subintervals would we like to really put in there if we could?
Infinity.
Infinity?
An infinite number of subintervals. It seems like if we were able to put in an infinite number of little rectangles in there, that should then give us an exact value for the area underneath the curve. The only problem is if we have an infinite number of them, they have a thickness of, or a width of 0, and then I'm just multiplying them all by 0. So we have a little bit of an issue there, which we'll have to come up with some way to deal with in the future. But everybody see that we could draw these rectangles on here and approximate the area underneath any curve and get a decent approximation. I mean, even with 3 subintervals, we were only off by a quarter with the midpoint rectangular method. So pretty good. So let's have you guys try to do this one using a midpoint rectangular approximation. We're going to see if you can come up with a good approximation all on your own for the area underneath 1 over x plus 1 on the interval from 1 to 9. Everybody think they could do that? 4 subintervals, and you're going to use a midpoint approximation.
Can we look at a graph?
If you wish, you can look at a graph. Yeah, sure. I could even pull up a graph if you wanted, just so you can see.
I just have a Desmos. Oh, okay. I have a Desmos tab open at all times at this point.
That's good. It's important. 1 over x plus 1 looks like this. We're looking from 1 to 9. So we want to know the area from here to here of this function. So what is that area? Looks like the function is decreasing, right? So if we were doing a left approximation, we'd have an overestimate. If we were doing a right approximation, we'd have an underestimate. But we're doing a midpoint approximation, so we can't really tell for sure what we have. So maybe that graph helps, maybe that graph doesn't help, I don't know. But you can all graph it on Desmos on your own and take a look at it, but I'll go back to the problem. So 4 subintervals, rectangular midpoint approximation. You guys think you could do that or no?
I mean, I could. I don't know how
Right.
good the thing would be.
Well, give it a try. All right, ready, go. Take 2 minutes and see if you can approximate that. And then we're going to see how accurate our answer actually ended up being. Ready, go. So we had 4 subintervals from 1 to 9. So that means from 1 to 3, from 3 to 5, from 5 to 7, and from 7 to 9. And if we're doing a midpoint, that means we want 2, 4, 6, and 8 to be the values that we plug in. And what is the width of each of the rectangles going to be? If we go from 1 to 3, 3 to 5, 5 to 7, and 7 to 9, it ought to be 2 for each of them, right? So all we then need to do is figure out the height of each one. So the width of each one is 2. And if we're plugging in 2, that should be a half plus 1, which will be 3 halves. And then if we're plugging in 4, that should be a fourth plus 1, which will be 5 fourths. And if we're plugging in 6, that'll be a 6 plus 1, which will be 7 sixths. If we plug in an 8, that'll be 8 plus 1, which will be 9 eighths. Those will cancel. This will make that into a 5 halves, 7 thirds, and a 9 fourths. And if we get a common denominator for those, what should the denominator be? It should be 12, right? So what did that come out to be? This will be 36 twelfths plus another 30 twelfths will be 66 twelfths plus 28. That'll be what, 94 twelfths plus another 27 twelfths. What is that? 94 and 27, right? Is 121. So 121 twelfths. And what did you say your approximation came out to be? Around what? Is that what you got?
I said around 10, but that's around 11. I said around 11, but that's around 10.
Yeah. Is that what you got or no?
I was 1 off. I did a dumb thing.
I see. All right. What does this approximate out to be? What is 121 over 12? 10 point something, right?
083.
083. Is it repeating on the 3? Yeah.
Yeah.
Okay. All right. Cool. So I will then tell you what the actual value of this is. Let's see. I have to figure it out real quick because I probably should have done that, but I didn't. The actual value of this is equal to the natural log of 9 plus 8. So somebody tell me what that approximates out to be.
Like 10.197224458.
Good enough. 10.197, right? So 10.083 repeating to 10.197. Pretty darn close, I would say. Wouldn't you guys say? It's pretty close.
Yes.
Yeah, pretty good approximation. And that's, that's over 8 units with only 4 subintervals. I mean, we hardly broke that down. I mean, if I'd made 8 subintervals, I'd have been even closer, right? Or if I made 1,000 subintervals, I'd be almost exactly correct already. Any questions on that? Everybody okay with that? All right. Let's see. Yeah. I think we better stop there because we're going to get into some stuff that's going to take a lot more time. We only got about 7 or 8 minutes left to go anyway. So, any questions on anything we did today? First off, just approximating areas underneath functions.